Welcome to the next video in the real analysis video series, and in this video I'm going to discuss my proof for this exercise. So we're going to say, suppose that a set X satisfies all the ordered field properties, right? So this is supposed to be kind of, any set satisfying all of the ordered field axioms except for the completeness axiom. So, this could be, in a sense, kind of any set. At least at the beginning of our analysis, we imagine that it could be any set. And then we further assume that it has the Lub property, and what we would like to do from that is to prove that it satisfies the completeness axiom. Okay, to show that it satisfies the completeness axiom, we need to consider two sets non-empty with one of them entirely below the other one. And so, since they're, non-empty and so on, we, just immediately get that any element of B is an upper bound of the set A. And from the Lub property, right, the Lub property says that whenever it is bounded above, then it has a least upper bound, right, it has a supremum. So we'll call that supremum alpha, right? We now know that the supremum of A exists, and we may call it alpha. And we're trying to remember, right, we're saying that if A is entirely, just like imagine a number line with A down here and B up here. And we have essentially just established that the supremum of A exists. And we're going to try to argue that this sup A is a value that, like in the completeness axiom, we called C, where C is, entirely, I'm going to just abuse notation here, but C is between A and B, so to speak, right? So that's a little bit of abuse of notation, but I think it very quickly communicates what I'm trying to get at. And so we need to show that this value C is in fact entirely above A, basically, but that follows immediately from the fact that the sup is an upper bound, right? That's just part of the definition of being the sup of a set, is that it is an upper bound. It's in fact the least upper bound, but for right now, all we need is the fact that it is an upper bound. So this side of the, inequality, even though it's an abuse of notation inequality, this side of the inequality is already satisfied by the mere fact that C is the sup of A. So how about this other side of the inequality over here? Well, we know B is non-empty. Let's pick an arbitrary element out of it. Now, we know that any element chosen out of B is an upper bound of the set A. I mean, we already remarked on that before, and you should make sure that that is still clear in your mind. But if we pick any element out of B, it is an upper bound for A. Well, alpha, or I guess here I'm calling it alpha. Oops, maybe that's not the best notation. I should call that alpha. Let's switch to calling that alpha. So that's alpha. So this alpha is the least of all of the upper bounds of the set A, and therefore it must be less than or equal to this value B. So, right, so we have that alpha is less than or equal to B because it's the least of all the upper bounds, where B is one of the upper bounds. But this is true for a generic B, right? Any B out of the set big B that you choose, meaning that alpha is in fact entirely below B, right? That it is a lower bound of B. So now we've justified the other side of the inequality, and we're done. We write the halmos. Okay, let's move on. So, here's a note. In fact, the above proves that sup A is a lower bound of B, possibly useful. One may, of course, use the same logic mutatis mutandis to show that inf B, and sometimes we write the parens, sometimes we don't, so don't worry too much about that. But inf B is an upper bound of A, so that you could prove basically the same way, just switching some of the things around inside the proof. And in fact, all of this parlays into a proof that sup A is less than or equal to inf B. I leave this as an exercise to the viewer. In fact, this is all part of an exercise at the end of the next section, exercise 16b from section 2.2.5. And I guess that's the note. Okay, let's get to another exercise. But first, let's say throughout the rest of this series, we will always assume that the set of upper bounds and lower bounds are always taken from the real numbers. I guess I've already remarked on that in an earlier video, but here we have it again. Okay, let's talk about this exercise. There are some very important soup properties, and every soup property has a corresponding inf property, basically, right? I mean, there is a kind of symmetry or duality between the soup and the inf, so that's to be expected. But I like to just state and do things for one of them, and then suggest that mutatis mutandis, the similar facts hold for the inf, for the dual. So in any case, we're going to focus for now on soup, and I'll leave inf facts for a later exercise. But these, I guess I should also, by the way, emphasize that soup and inf, these are the bread and butter. These are the core, tools that we will use throughout analysis. It may not be obvious now just how important they will be throughout the entire study, but they will be. And so you want to start getting good at using them. And so these theorems that we're about to prove, I mean, they're an exercise in proving theorems for sure. But they're not just that, they are extremely useful facts that we will refer to throughout the rest of the course. So, and by the way, I like exercises that do double duty. I like to pick exercises that are a good exercise on the one hand, and also we use these results for later studies and exercises. So let's give, so a lot of these theorems that I'm about to state give some alternate characterizations of the objects involved. So for instance, soup x actually just is the same thing as negative inf negative x, and that's going to be one thing to prove. This is not really an alternate characterization. This is just a sometimes useful fact that the soup, if x is a subset of y. Oh, by the way, Zorich uses this, I think, doesn't he? Or no, because I think you're seeing that I wrote some of these notes. I wrote some of these notes when I was working from the textbook by Pugh, and then I switched to the textbook by Zorich. And so Pugh uses this to mean subset, but Zorich, I believe, uses this to mean subset. And so I should edit that and say that if x is a subset of y like that, then soup x less than or equal to soup y. So that's just a generally useful fact. This is like a kind of an alternate characterization because the soup is always equal to negative inf negative x. So that's kind of an alternate characterization, which is sometimes useful. So by the way, there's another way to think about this, right? If you just move the negative to the other side, then you can almost think of this as so the rule basically, or a rule, is that a negative on the outside of a soup can move inside so long as you flip it to inf. And in fact, you can read the rule in the other direction as well. A negative on the inside of an inf can move outside so long as you flip it to a soup. And of course, there's going to be dual rules where, the soup goes here and the inf goes here. And that is also true, and you can also prove that, but I won't do that in the next video. I'm not sure I'll do it at all. I think I leave that as an exercise to the viewer. But in any case, okay. So that is part of that's one of the things that you are to prove. Then we can also define what it means to take a single real number c, right? C is just an individual real number, x is a set of real numbers, and we define it in a somewhat understandable way that if you do c times x, what we mean by that is that you take all the elements of big X and you multiply them all by your number C, right? So it's just notation for a thing that we do sometimes. The theorem, now that we have defined that, the theorem that you are to prove is that if C is non-negative, then C can simply move straight over a soup and inside the soup. If C is negative, then it moves inside but flips to inf. And let alpha be a real number, and then we can say that alpha is the soup of x. I guess, I don't know if I already established that x is a non-empty set bounded above. I think I did, but in any case, throughout this whole problem, you should assume that x is a non-empty set of real numbers bounded above. And so we'll say that soup x is alpha if and only if alpha has the following properties. It is an upper bound of x, and here's the interesting one, and this is pretty useful. This is especially characteristic of an analytic thinking. For every positive real number epsilon, the number alpha minus epsilon is not an upper bound. So this is a pretty useful theorem, and we'll be using this to make proofs later on easier. So yeah, there you go. There's a bunch of stuff to prove, and my solutions will be in the next video.